Okay, so we would like to discuss the space C0, another Banach space, and here's what this is. So this consists of all sequences that their limit, whose limit is equal to 0. Okay, and we impose the same norm that we had for L infinity. So sometimes we refer to it as the infinity norm or the sup norm. So the every sequence that tends to 0 is bounded. So from that, we can argue that the same norm that we had for xn makes sense here too. So having said this, this means that this establishes that C0 is a subspace of L infinity. So with this norm, C0 is a subspace of L infinity. And that means right away that it's a norm linear space. Okay, please note that it is a vector space. So if you take two sequences that tend to 0, their sum is a sequence that tends to 0. And of course, the scalar multiple of any sequence that tends to 0 also tends to 0. So it is a vector space. And that means that we get for free that C0 is a norm linear space. So now, in order to show that it is complete, we can either do it independently or we can do it by showing something else. We can show that to show that it is a Banach space, it suffices to show that it is a closed subspace of L infinity. Why is that? Closed means by definition, well, almost by definition, depending on how you define closed sets, that the limit of any sequence whose terms belong to the set also belongs to the set. So in other words, closed sets do not let their sequences converge outside of them. So if you have a Cauchy sequence in C0, then certainly, since the norm is the same, it's a Cauchy sequence in L infinity. L infinity is a Banach space, so C0, so the sequence will have a limit in L infinity. And the only thing that matters is that this limit also belongs to C0. So we have to show that the limit of sequences that have limit 0 also has limit 0. Okay, and then we will be done. So to show this, it's enough to prove that if xm tends to x in L infinity with xm being in C0, then x is also in C0. Okay, and of course, here we have that xm is simply the sequence xm comma n for n in n, and x is the sequence xn n in n. Okay, so how do we do this? Well, as usual, let epsilon be greater than 0. And we need to show that there exists n naught in n such that if n is greater than n naught, then xn is less than epsilon. Okay, that's what it means for a sequence to tend to 0. Okay, but we said that the sequence xm, the sequence of sequences, xm converges to x. So there has to be, there exists m in n such that xm minus x in absolute, in norm is less than epsilon over 2. Okay, in fact, after a certain point, all the xm's satisfy this. So this is, it is true for m large enough. But I just need one of them. Okay, so what does that mean? That means that the supremum for n in n of xm comma n minus xn is less than epsilon over 2, which means that xm comma n minus xn is less than epsilon over 2 for n in n. Okay, but now the sequence xm comma n tends to 0. However, the limit as n tends to infinity of xm comma n is equal to 0, which means that there exists an n naught in n such that for n greater than n naught, let's give ourselves a little space. I mean, we have that xm comma n is less than epsilon over 4. Okay, I'm saying epsilon over 4, maybe epsilon over 2 will, but you know, this is okay. So if I take now, so if n is greater than n naught, then if I take xn, this is the same thing as xn minus xm comma n plus xm comma n. By the triangle inequality, this is less than or equal to xn minus xm comma n plus xm comma n. The first is less than epsilon over 2. The second is less than epsilon over 4, which is, of course, is less than epsilon for n greater than n naught, which is exactly what we wanted to show. Hence, the limit as n tends to infinity of xn is equal to 0. This almost ends up being chasing definitions around. It's a very simple thing to show. And that's all. Thanks for watching.